It's funny, you listen to anyone talk about the AI boom these days, and it is almost always the exact same conversation.
Oh, totally. It's all software.
Right. Everyone is just absolutely obsessed with the software side. Like the newest updates to ChatGPT, or, they are laser focused on those massive multi-thousand-dollar GPU chips that actually process the data.
Yeah, the NVIDIA chips get all the glory.
Exactly. But I bet you listening to this have noticed that almost no one is talking about the actual physical plumbing that makes all of this possible.
Is the great blind spot of the current tech narrative, honestly.
Yeah.
I mean, we treat the cloud and AI in general like it's just this, I don't know, ethereal magic floating up in the sky.
Like it doesn't exist in the real world.
But it is deeply, stubbornly physical. It relies on physical hardware that is quite literally being pushed to the absolute limits of physics right now.
And so that is the mission of today's deep dive. We are going to decode this invisible hardware war powering the AI boom.
The plumbing.
The plumbing, yes. Specifically, we're plunging into the wildly complex world of optical infrastructure. Because right now, despite the seemingly insatiable global demand for AI, tech investors are suddenly experiencing a massive, massive financial freakout.
Yeah, the people actually funding the plumbing are panicking. It's quite a paradox, really.
It makes no sense on the surface. The demand for AI processing power is completely unprecedented.
Right, yet the financial market surrounding the physical infrastructure is incredibly jittery. They are reacting wildly to, rumors and these half-understood technological shifts.
So to figure out what's actually happening behind the scenes, we brought in a really fascinating stack of sources to pull from today.
A really diverse stack, too.
Yeah, we're looking at a recent financial market analysis piece that highlights these sudden investor jitters over slowing hyperscaler spending.
Those are the big guys, Microsoft, Google, Amazon.
Exactly. We are also diving into a deeply technical 2025 growth strategy deck from the Japanese infrastructure giant Sumitomo Electric.
Which is full of some crazy engineering details.
Oh, it's wild. And finally, we have this rather fierce clarification announcement from July 2026, straight from the optical module titan Zhongji Innolight.
They were not happy.
No, they were aggressively defending themselves against a total storm of market rumors.
And that combination of sources really gives us a perfect cross-section of the landscape. I mean, we can look at the raw physical constraints outlined by Sumitomo, the market panic from the financial press, and then
the actual on-the-ground manufacturing reality.
Exactly, from Zhongji Innolight.
Okay, so let's unpack this, because the way I'm reading these sources, building the AI revolution right now is kind of like planning a massive futuristic megacity, but suddenly realizing everyone forgot to upgrade the water pipes.
That's a great way to look at it.
The data is the water, and right now, the pipes are practically bursting under the pressure.
They are. And to understand why investors are suddenly panicking over those pipes, we first have to look at the physical limitations constraining that megacity.
Okay, where do we start?
It starts, fundamentally, with a massive, unavoidable power problem. Sumitomo Electric's data lays this out in incredibly stark terms.
I saw this chart, yeah.
If you look at global data center power demand, in 2022, it sat at about 500 terawatt hours.
Which, just to pause there to put that in perspective for you listening, is already an unfathomable amount of electricity.
It's massive.
That's essentially the energy consumption of entire industrialized nations, just for data centers.
Right. And driven by the emergence of generative AI and these massive large language models, that demand is projected to nearly double.
To what?
They're saying it'll hit an astounding 950 terawatt hours by 2030. To facilitate that, server purchases are growing at a rate of 29% every single year.
Wait, 29% year over year?
Every year.
That is compounding exponential growth on top of a base that was frankly already straining the grid.
And here is the physical bottleneck the industry has hit. You cannot infinitely draw that much power in one single location.
Because the grid would just collapse?
Exactly. The electrical grid in any given city simply cannot handle a concentration of demand like that without causing rolling blackouts. So, the hyperscalers, those massive cloud providers we mentioned, are being forced to physically spread out their data centers.
They can't just build one giant mega campus anymore.
No, they are rapidly moving away from single monolithic campuses and creating what the industry calls edge DCs, or edge data centers.
Because they have to literally chase the electricity. I mean, they have to go where the power is actually available, rather than trying to drag all the power to one central spot.
Spot on. And this brings us to a critical industry concept that Sumitomo highlights in their strategy deck. It's called watt-bit coordination.
Watt-bit coordination.
Yeah,
Okay.
it's this incredibly complex logistical dance of balancing where the power is, the watts, with where the computing actually needs to happen, the bits.
You have to coordinate the two perfectly.
Exactly.
So, what does this actually mean in practice? Is it kind of like trying to plug 30 heavy-duty space heaters into one living room, instantly blowing the main fuse and deciding, okay, you have to put the heaters in completely different houses down the street?
Right, but they still need to work together.
Exactly. But now you need these incredibly long, highly efficient extension cords to keep them all synced up and functioning as one single heating system.
And that is exactly what it's like. That dispersal for power procurement creates massive physical distances between the separated data centers.
How far are we talking?
We are talking about connecting buildings that are up to 120 kilometers apart.
Wow.
But because they are running distributed AI training models, they have to act like they are in the exact same room. The latency has to be functionally zero.
Which means you can't just use standard internet connections.
Not at all. That requires ultra-high density optical cables to carry the data back and forth.
And 120 kilometers is no joke. I mean, digging trenches to lay down new massive fiber optic pipelines between cities takes years, and it costs an absolute fortune.
Which is why Sumitomo has a very specific solution for this exact problem in their deck. Because you're right, you can't just easily dig up 120 kilometers of Earth to lay new massive pipes every time AI demand spikes.
So what do they do?
They've developed a 1728 fiber count air-blown cable.
Okay, air-blown cable. Break that down.
What this does is fit double the amount of individual glass fibers into the exact same 18-millimeter existing underground ducts that are already in the ground.
Hold on, I need to visualize this. They are shooting a bundle of over 1,700 microscopic glass threads.
That are each fractions of a millimeter thick.
Right. Through miles of underground pipes using compressed air. How does that not just shatter the glass instantly?
It sounds chaotic, I know, but it's actually an incredibly precise aerodynamic process. The cable jacket is specially engineered with a low-friction aerodynamic surface.
Okay.
So when they pump high-volume compressed air into the duct, the air actually lifts the cable off the bottom of the pipe. It reduces friction to near zero. It practically floats the cable through miles of existing underground infrastructure.
That is genius.
Yeah, by doubling the fiber count but keeping the physical cable small enough to use existing 18-millimeter pipes, they effectively cut construction time in half. You get twice the data capacity between these spread-out data centers without having to dig a single new trench.
Okay, so the air-blown glass threads solve the problem of getting the data between the buildings. They are the giant extension cord. But looking at our sources, they're saying it's not just the long distances that are stretching to the breaking point.
No, not at all.
The plumbing inside the data center itself is also failing under the weight of AI.
If we connect this to the bigger picture, the entire architecture inside the building is fundamentally changing. The industry is rapidly shifting from what they call a scale-out model to a scale-up model.
Meaning what, practically?
The most significant immediate consequence of this shift is that the short cables connecting the servers directly to each other are transitioning away from traditional copper wiring to optical fiber.
Wait, here's where it gets really interesting to me. So, copper is officially dead inside the data center.
Pretty much, yeah.
Are we basically saying electricity itself, like actual electrons moving over a copper wire, is just too slow or too leaky to handle generative AI at this scale?
Yes. When you push electricity at extreme frequencies over a traditional copper wire, you encounter massive signal degradation over very short distances.
The signal just fades.
Exactly. But worse than the signal loss is the thermal byproduct. Pushing that much data via electricity generates an enormous amount of heat.
And servers are already running hot.
Right. And the speed requirements for these intra-data center connections are just staggering right now. We are seeing a rapid progression from 400G speeds to 800G to 1.6T, and eventually they're projecting 3.2T.
1.6 terabits per second. Just wrapping your head around that volume of data moving between servers in the blink of an eye is difficult.
And at 1.6 terabits per second, if you try to use copper, the wires will literally melt the servers.
Literally melt them. That's terrifying.
Yeah. Only light photons moving through pure glass can carry this much data this fast without generating catastrophic heat.
But the plugs for light are way more complicated than a standard copper wire, right?
Exactly. To achieve those speeds using light, the physical optical components have to shrink dramatically to fit inside these tightly packed server racks. Sumitomo is rolling out a 24-fiber compact MMC ferrule that uses a double-layer array configuration.
Wait, what actually is a ferrule? We throw these terms around, but are we just talking about, like, the plastic plug at the end of the cable that clicks into the server?
Essentially, yes.
Yeah.
Think of the ferrule as the ultra-precise mechanical housing at the very tip of the connector.
Okay.
When you are connecting 24 separate microscopic glass fibers to a tiny laser on a chip, they have to align perfectly.
How perfect is perfect?
If the alignment is off by even a single micron, which is a fraction of the human hair, the light misses the receiver and the data is completely lost.
Oh, wow. So there's
Yeah.
zero margin for error.
None. And Sumitomo's new compact MMC ferrule manages to align a double layer of these fibers, achieving 6 times higher density, while simultaneously shrinking the physical footprint of the connector to 1/3 of its previous size.
So the data literally has to become light, and the physical plugs have to become these microscopic masterpieces of engineering.
And this transition to light is causing a massive shift in the types of laser chips being manufactured, too.
Oh, so.
Well, according to the Sumitomo deck, the market for continuous wave laser diodes, or CWLDs, is expected to jump from just 24% of the market in 2024 to a dominant 69% by 2028.
I'm trying to picture how that works. Why a continuous wave laser? If data is just ones and zeros, shouldn't the laser just be flashing on and off really fast?
Under normal circumstances, yes, that's how traditional fiber optics work. But when you are trying to transmit 1.6 terabits per second, turning a tiny laser on and off billions of times a second creates way too much thermal stress.
Oh, so the laser would just burn itself out almost instantly.
Exactly, it would fry. So instead, they are shifting towards something called co-packaged optics, or CPO.
Okay, CPU.
With CPO, you use a continuous wave laser that just stays turned on, firing a steady, unbroken beam of light.
Just a solid beam.
Right. That continuous light source is brought directly onto the silicon processing chip itself, and then incredibly fast silicon modulators essentially chop that steady beam of light into ones and zeros.
Oh, so the laser doesn't turn off, the modulator just blocks it or lets it through?
Precisely. It is the ultimate hyper-efficient integration of light and processing.
Okay, so the macrophysics demand it, and the microengineering is delivering it. You've got 1728 fiber cables underground, microscopic continuous lasers on the chips, all working to handle this 950 terawatt-hour beast that is AI.
It's a massive undertaking.
Right. So if demand is this explosive, why did the financial markets just completely freak out last month? Because according to our sources, an optical infrastructure giant stock basically fell off a cliff in a single day.
Yeah, this brings us to the July 12, 2026 clarification announcement from Zhongji Innolight.
Right.
Their stock absolutely tanked. It saw an over 8% drop on July 10th, and it was entirely driven by the rumor mill.
An 8% drop in one day.
Yeah. The market was flooded with claims of a severe Q2 earnings miss, accusations of deliberate stock price suppression, and, most crucially for our discussion, rumors about 1.6T demand delays.
So investors thought the AI boom was stalling out.
Exactly. There were even whispers spreading that there were blockades of upstream glare filter materials halting production.
An 8% drop for a trillion yuan market cap company is an absolute bloodbath. I mean, wealth is just vaporizing based on whispers. So how did Zhongji respond to the bleeding?
With a total and fierce denial. I mean, they actually held an emergency call with over 100 financial institutions to set the record straight and calm the panic.
What was their main argument?
Their core argument was that overall 1.6T demand has absolutely not dropped. What the market is misinterpreting is a structural shift in who is buying the modules.
Okay, a structural shift. What does that mean in plain English for the listener?
It basically means the customer mix is changing, but the total pie is exactly the same size.
Ah.
Some specific clients did reduce their individual 1.6T orders, but simultaneously, newly added cloud service providers and emerging AI large model companies stepped up and raised their demand.
So it balanced out.
Completely. The total volume remains completely intact. Furthermore, Zhongji pointed out that demand for the previous generation, the 800G modules, actually exceeded their expectations.
Wow. Okay.
And they also highlighted that in China's domestic market, AI data center demand is growing rapidly, concentrating very heavily on those 800G and 400G products.
Okay, I have to push back here. Just playing devil's advocate for a second.
Sure.
If a billion-dollar company holds an emergency late-night call with over 100 financial institutions just to say, hey, everyone, we're totally fine, nothing to see here, please don't panic, doesn't that usually mean there's fire where there's smoke?
It's a fair point.
Right. Like, are we absolutely sure they aren't just trying to PR spin the loss of a massive mega contract to a competitor?
This raises an important question, and honestly, your skepticism is entirely valid. When a company acts that defensively, you really have to look past the PR statements and look at the underlying manufacturing reality.
And what does the reality say?
The hard data supports Zongji here. You have to understand, high-end optical modules are not just a simple assembly industry. It's not a business where anyone can just rent a warehouse, set up a factory line, and undercut a contract.
So it's not just snapping Legos together on an assembly line.
Not at all. The barriers to entry are incredibly deep and technically brutal. We're talking about mastering silicon photonics and perfectly executing coherent optics.
Stop right there, coherent optics. I see this term everywhere in these infrastructure reports. What does that actually mean?
Okay, so in traditional fiber optics, you transmit data by just flashing a light on and off, which is amplitude. Bright is a 1, dark is a 0.
Simple enough.
But coherent optics is entirely different. It uses highly complex digital signal processors to manipulate not just the amplitude, but the phase and the polarization of the light wave itself.
Wait, so you're twisting the light wave.
Exactly. It allows you to pack exponentially more data into a single pulse of light, allowing it to travel vastly further without degrading. But the manufacturing yield rates for these components are punishing.
Meaning they get a lot of duds on the factory line.
Yes, getting it right at scale without massive defect rates is incredibly difficult.
So it's not that clients wouldn't want to jump ship for a cheaper competitor. It's that there essentially are no competitors who can reliably build this stuff.
Precisely. Only a very small handful of manufacturers on the entire planet can actually deliver 1.6T optical modules at scale. Zongji explicitly stated their order book is completely full through the entirety of 2026.
With some visibility into 2027, right?
Yes. Customers can't just easily jump ship to a competitor because the competitors simply do not have the capacity to deliver. The manufacturing mode is miles wide.
That makes perfect sense. The capacity to actually build the physical hardware is the ultimate kingmaker here. But looking at the sources, investors weren't just spooked by delayed orders, right?
Yeah, there was more to it.
There was also this technological rumor that was terrifying them, something about optical modules being rendered entirely obsolete overnight.
Ah, yes. The Corning glass bridge rumor.
Right.
The financial market panicked because a narrative took hold that a new glass bridge technology developed by Corning was going to completely bypass and kill Zongji's optical module business.
So investors panicked because they thought Corning just invented like a technological teleporter that makes cars obsolete.
Exactly. But Corning didn't invent a teleporter. They just created a specialized component that allows the current engine to run at the extreme temperatures AI requires.
So it's just a misunderstanding?
Total misunderstanding. The market's complete lack of technical understanding created massive financial volatility. Zongji had to painfully explain to investors that Corning's glass bridge is simply a new coupling component designed for that co-packaged optic system we discussed earlier.
The CPO.
Right. It is a piece of the puzzle that helps read the light. It is not a substitute for the optical module itself.
Got it.
Even if glass bridges become mainstream, Zongji's technology portfolio adapts to it and incorporates it. It isn't destroyed by it.
It really highlights how disconnected the financial market can be from the actual physics of the technology they're betting on. I mean, people are trading billions of dollars in stock based on headlines about glare filters and glass bridges that they don't fundamentally understand.
It's wild. And if you look at the physical actions of these infrastructure companies, rather than the market rumors, the reality is clear.
What are they actually doing?
Both companies in our sources are heavily doubling down on physical capacity. Zongji pointed out that their new factory in Thailand is humming along with zero labor shortages, and they're actively expanding capacity to create a buffer for even more global orders.
So Zongji is building buffer capacity in Thailand to weather the storm. But what about the raw materials? You can't just spin up a massive manufacturing line for ultra-pure glass and lasers overnight. How is Sumitomo reacting to this?
Sumitomo is vastly accelerating production. Their 2025 growth deck shows that their optical connector capacity is being ramped up by 7 times.
7 times.
Which, notably, is 5 times higher than their previously announced target.
They are rushing it.
Absolutely. Furthermore, their production capacity for NEP substrates and optical devices is up 2.4 times.
Wait, Indium phosphide? Why are
Yes,
they scaling up exotic materials like indium phosphide? Why not just use standard silicon to build these chips like every other computer part on Earth?
because standard silicon is an indirect band gap semiconductor.
Okay, translation, please.
In simple terms, it is notoriously bad at generating light. If you pump energy into silicon, it releases heat, not photons.
Oh, which goes back to the melting server problem.
Exactly. To fire the ultra-fast continuous wave lasers we need for 1.6T data speeds, you have to use exotic, complex materials like indium phosphide that can efficiently turn electricity directly into high-powered light.
That makes sense.
And you do not spend millions scaling up the physical footprint for indium phosphide fabrication if you think demand is softening.
Right. It takes years of planning to build those fabrication plants. And didn't Sumitomo just get a huge nod from the king of AI chips themselves?
They did.
Oh,
Sumitomo was recently selected as an official NVIDIA Silicon Photonics ecosystem partner.
wow.
This proves that these legacy hardware infrastructure giants are not being left behind by the AI software boom. They are deeply structurally embedded in the next generation of AI. NVIDIA knows they cannot push their GPUs any further without the optical plumbing keeping pace.
Okay, let's bring this all home. Why should you, the listener, care about any of this?
Well, I think it fundamentally changes how you look at the technology you interact with every single day.
It completely reframes it.
The next time you open up an AI tool on your phone, ask it to write a complicated email or generate a high-res image, remember that the cloud doing the work isn't a cloud at all.
It is a massive, incredibly complex physical loom of ultra-pure glass threads stretching across continents.
It's microscopic indium phosphide lasers firing steady beams of light, silicon modulators chopping that light billions of times a second, and 24 fiber connectors battling the absolute physical limits of heat and distance inside a data center hundreds of miles away.
All just to get you an answer a millisecond faster.
Exactly.
And that really is the ultimate takeaway here. Financial markets will always panic over quarterly shifts, rumors of order delays, and misunderstood tech headlines.
Right, the daily noise. But underneath all of that, the actual physical build-out of a 950 terawatt-hour global AI infrastructure is moving forward relentlessly. The hardware war is very real and is being fought every day in the trenches of optical physics.
It's the water pipes of the futuristic megacity. And those pipes are getting smaller, they're pushing exponentially more data, and they're increasingly made of pure light.
It's beautiful in a way.
It is, which leaves me with one final thought for you to mull over as you go about your day. If our entire global intellect and seemingly our entire future economy are becoming utterly dependent on microscopic light modulators and ultra-pure glass threads just to keep up with AI's insatiable hunger for data, what happens when we finally hit the physical speed limits of light itself?
That's the real wall.
Right, where do we go from there?
A fascinating question for another day.
Until next time.